Sure. All right. So, yeah, welcome back to this weekly book club meeting. Today we're going over chapter 8 in the Irwin text. So, that's on AC steady state analysis. Right. And just going to quickly jot down these learning goals here so that we're aware of them. So, the first one is we want to kind of understand basic characteristics of sinusoidal functions. All right, understand sinusoidal functions. 8-2. We're going to learn how to perform phasor and inverse phasor transformations and draw phasor diagrams. 8-3. Um, calculate impedance and admittance for our basic circuit elements. Turn off this writing aid. I don't know why it always pops up. So 8-4, we're going to learn how to combine impedances and admittance in series and parallel. And 8-5, so we're going to draw frequency domain circuit for a given circuit with the sinusoidal source. So I'm just going to write draw frequency domain circuit, and we'll get into kind of what that looks like, as far as the source goes, because so far we've really only been looking at DC sources. And last but not least, we're going to, well, so they have this part about knowing how to apply circuit analysis techniques to frequency domain circuits, but I'm not going to jot that down. I don't think we'll get to that. But basically, it's a lot of the techniques that we've already learned kind of apply to these sinusoidal AC circuits. All right, so kicking things off with sinusoids. Um, and I don't want to spend too much time on this because presumably you've seen sinusoidal functions before, but I just want to, kind of formally define them before we get into it too much here. So this is a regular sine wave, right? So it starts at 0, it goes up to 1, and it goes down to -1, and this happens in a single cycle, 2 pi. So we're going to more generally look at a sinusoidal function as having an amplitude. We'll call that capital X sub m, kind of like this maximum value of our general sinusoid, and it has a minimum value minus capital X sub m. Um, and so it's going to complete a cycle more generally in a period. And so we like to define the frequency as 1 over the period. All right, so if we're looking at time here, the time that it takes to complete this full cycle, we'll just call that, generally speaking, the period. And we can also define this in terms of angular frequency, omega. So this is going to be 2 pi times f, right? How many times we're completing a full cycle, 2 pi, um, looking at that frequency. So in terms of the actual period, the time period, this is going to be 2 pi over t, right? Um, and the last thing that we'd like to kind of draw our attention to is the possibility of a phase shift. So if I have a sinusoidal function and there is some amount of phase shift, right? So maybe this is happening sometime theta in advance. Um, we say that this dashed line function is leading, right? The normal sine wave. Um, and so generally we define this function x of t, right, which is this dashed line, is capital X sub m, right, where this again is our magnitude times sine omega t plus r theta. And again, so that theta is how much phase is shifted, right? And for positive theta, this is happening before the regular sine wave, right? If theta was negative, maybe over here, then it's happening after, and we say that that x of t is lagging the regular sine function. Um, so hopefully that should be somewhat review. It's and feel free to stop me if you have any questions on that, but that is kind of all I wanted to talk about here. There are some example problems, and maybe it would be worthwhile to go through one. I did write down that I wanted to go over one, so maybe we'll just kind of run through a quick example. So this is 8.2, and we want to determine the frequency and phase angle between these two functions. So our first function, v1 of t, is given by 12 times sine 1000 t plus 60 degrees. And our v2 of t is given by minus 6 cosine 1000 t plus 30 degrees. And so these are with units, volts. Um, so the first thing that you typically want to do when you're looking for the phase between two things is we want to make sure that they have the same frequency, right? And I guess the first part of this question was to actually go and actually determine the frequency, and you can see that both of these voltage functions have a 1000 T term here. And if you recall the formal definition of the sine wave, which we had back here, this is times omega t, right? So this 1000 is actually our omega.
Hmm.
So this is omega. So if we look for the actual frequency, then we can find that this frequency is 1000 over 2 pi hertz. So that's our frequency. Um, and then the next thing that we want to do is determine the phase. And in order to actually determine the phase, we need to actually get these two functions in terms of each other effectively, right? So V2, we're going to turn that into a sine function. And then we're also going to try to get the magnitude to um, match what we had up there, right? At least um, being positive in the sense of it needs to be positive. So we're going to start off with our original V2 of t, and we're going to recall that in order to get cosine from sine, we're going to adjust the phase by, I want to say this is 90 degrees, right? So we're going to subtract 90 degrees? No, sorry, I'm missing out here. Oh, sorry, it's 180 degrees. Yeah, it goes to show how much I prepared for this. So we're adding 180 degrees in order to get this cosine term into a sine. So hopefully that should be pretty clear. Um, so I'm going to add 180 degrees to my phase shift here. Sorry, and this is going to be sine. So if I do 180 plus 30 degrees, I should get 210 degrees here. And next thing we want to do is to turn this magnitude into positive, right? And in order to do that, we can kind of pluck out what do they do here? They're using this equation 8.7. Yeah, so here they're adding 90 degrees. Sorry, so I got those mixed up. So if I phase shift this guy by 90 degrees, then I can get my positive magnitude out of there. Um, all right, cool. So now we have, hopefully that makes sense. Feel free to stop me if that doesn't make sense.
Yeah,
Basically, there,
it's all
yeah,
good.
yeah, okay, you're good. All right,
Yeah.
cool.
It's like pretty much review. So
Yeah,
yeah.
right. Okay, good. Um, cool. So now we've got these two, kind of more or less in terms of similar functions, and we want to determine the phase shift between them. So this first guy is 60 degrees, or V1, so that's going to be our reference angle. Um, so in essence, what we do is we take the reference angle and we subtract off, right, the next angle, and we find that this is minus 240 degrees, which kind of, if you look at the whole circle, this is the same as, right, if I go from 0 go to minus 240, this is actually just the same as 120 degrees. So these two functions are 120 degrees apart. Um, and I think that's all they wanted to determine. Yeah, so they wanted to find the phase angle between these guys, right? So this is kind of like going to be our theta.
Wasn't V1 12 sine theta,
Yeah,
not
sorry about that.
6?
So that's not
Okay.
going to matter in terms of the phase, but that's a good point. Yeah. So that's our um, the angle between these two guys, and they didn't really label it anything. I'm just going to call it theta. Um, and one way to look at this is that V1 is leading by 120 degrees, or you could also say that V2 is lagging, right? So I'll say V1 leads V2 by 120 degrees. And so if I were to actually draw this out, right, or what is our first phase shift? So that's 60 degrees. Um, right, so I'll just start off by drawing a regular sine wave. I'm going to phase shift this guy, I don't know, by 60 degrees. I'll draw it maybe in blue here. So let's just call that 60 degrees. All right, and so it's going to start going up, go down. And then our other guy is, well, doesn't matter. So V1 is leading V2 by 120 degrees, right? So if this is 60 degrees, I go another 60 degrees this way, I've got 120 degrees. Um, and again, so like you had mentioned, the magnitude of V2 is half, right? So if I draw that in, it'll be kind of like half, something like that. Um, obviously that's not, I have no idea. All right, something like that. You get the point. I'm not great at sketching things, but yeah, that's just one example. Um, and it'd be helpful if you kind of had a plotting tool to plot all these things. MATLAB does a good job, or just kind of there's some other like Desmos online tools, but that's good there. Um, all right, so the next thing we want to talk about are sinusoidal and complex forcing functions. So now that we've formally defined sinusoids, we can look at sinusoidal forcing functions. And I do like that they open. So let's kind of just formally define that. So for linear systems, if we have a forcing function, right? And again, before we've had constant forcing functions, which are just kind of like the DC sources that we looked at before. But now we're going to have forcing functions of this form where it has some magnitude, right? So if I'm looking at the voltage, a voltage source again, it's got some magnitude V of t. Sorry, they've defined it as, not as V of sub m. They've defined it as A sine omega t plus theta. Then we'll have it. There will be responses of the form I of t is given by B sine omega t plus phi. And so one thing kind of important to note here is that these, right, the frequency stays the same. Um, right, if we're driving a linear system with some kind of sinusoidal source, the frequency is going to be the same, no matter where you are in the circuit, but the phase angle will differ, right, all over the place. So the phase angle of my forcing function is given by just this arbitrary theta value. But again, the response, which you can kind of look at in terms of current, will be a different phase. And here they've got it as an arbitrary number phi. Um, all right. So the next thing we want to look at here.
RJ.
Yeah, what's up?
And so like when they say the response of the form, does like response kind of mean like the behavior of the circuit based on the forcing function?
Yeah, exactly. And I mean, you could have a current forcing function, right? There's nothing stopping us from having that. They've just written it here, right? If we apply a voltage, we're going to expect to see current, right?
Hmm.
We will see voltages appearing all over the place as well. But generally speaking, those voltages are rising because we have current flowing. Um,
Gotcha.
yeah.
All right, cool.
So yeah, you apply one, you get the other out, basically. Um, all right. So moving on to this example, and I'm actually not going to walk through this entire example, but I'm going to draw out the circuit. So this is the circuit that we are looking at, and they use this as an example to demonstrate why um, it's not necessarily feasible to use differential equations if we don't have to. Um, right, so this is the circuit that they're analyzing, and it's just, very simple circuit just consisting of a resistor and an inductor, right? And if you go through the math, just using the form of differential equations that we had looked at before, right? So kind of just we start off KVL, we've got this Vm cosine omega t. Right? If I go around this loop, I have R I of t plus L di of t by dt. And generally speaking, when you have um, a non-constant forcing function, right? We had looked at kind of how to go about solving differential equations for constant forcing functions before. But it turns out, right, if you have this cosine or this kind of like a complex forcing function, it becomes pretty difficult to solve the differential equation. And if you can take a look at the textbook just to see how to go about doing so. Um, but to give you some context, it takes them about a page and a half of math just to solve this really simple circuit. And so we're not going to do that, right? That's kind of like the motivation for why we use this transformation that we're going to learn about soon. But I'm just going to go ahead and move on here. So we use Euler's function, or I guess the or Euler's equation here. And you might have seen this at some point in math, but maybe not. So Euler's equation is given by E raised to the j omega t equals cosine omega t plus j times sine of omega t, where j is the square root of minus one. Um, and so this is a complex function and it has a real part. We'll denote it by RE. So the real part is cosine omega t, and it's got an imaginary part, which we'll denote by IM. And this is sine of omega t. All right, and generally speaking, whatever you have this j multiplying, that's going to be your imaginary part. And then whenever you have multiplying just, just by itself here, I guess, is kind of like the real part. Right, so it's got a real part and it's got an imaginary part. Um, and it turns out that by using Euler's equation, we can greatly simplify differential equations just by nature of, having these derivatives out here. It kind of makes the analysis a lot simpler. And we'll kind of get into what that looks like here. But generally speaking, our approach is going to be the following. So we'll kind of choose forcing functions, choose complex forcing functions, and not just sinusoidal. And then we'll do our analysis and then take the real part of the answer. And so we'll kind of look at what this looks like in practice. So I do want to kind of just jump into an example here that they've got. Um, so this is going to be example 8-8.4. And again, we're looking at the exact same circuit, right? Where we've got a resistor and an inductor. And instead of driving this with a cosine function, we're going to drive it with v of t given by v sub m e to the j omega t. Um, and right off the bat, they tell us that we're going to express the response, well, as having the form I sub m e to the j omega t, j times the quantity omega t plus phi, right? So the current will have some phase angle associated with it, um, which they've denoted as phi. All right, and so we'll go ahead and kind of crank through the analysis again, right? So just doing our KVL. around that loop. So we've got v sub m e to the j omega t. And instead of, right, this function of time, our current, well, it's still a function of time, but we know it now to have some complex behavior, right? So this is going to be times r. Oh, and I didn't quite give myself enough space here. I'll move it down. Plus L times d by dt. I'm going to take the derivative of my complex current here. And if I go through and take that derivative, oops, oh my goodness, I get sorry, so let me kind of step back here. I guess they're just the j omega. Yeah, okay, that makes sense. Sorry, so I was trying to figure out how to take that derivative in the first place, but if you kind of just realize that um, when you have e to the j omega t plus phi, this can be broken up into e times j to the omega t times e to the phi, right? Where this is not a function of time. And so if we take a time derivative, then that won't have any contribution to the derivative, right? This is just um, a constant, more or less. Right? So if I take this derivative, then a j omega pops out. So I've got j omega I m e to the j times omega t plus phi. All right. So there is our KVL around this loop. I can realize that um, these e to the j omega t terms can be canceled out, right? So I'm left with Vm is given by Im e to the phi times r plus j omega L Im e to the phi. All right. And then if we want to solve this for our current, which is kind of what we're looking for at the end of the day here. So this is going to be given by, oops, what did I miss my J's here? Sorry, missed these J's. This is going to be Vm divided by R plus j omega L. All right. And at this point, obviously it looks a little bit more complex than what we've done before. Um, literally it has a bunch of complex numbers going around. But this turns out to be a lot more simpler of an approach than what we were doing before with all the differential equations. Um, and so now we have this expression, right, this equation for the current. Um, and what they go and do here is they convert it kind of into the polar form. Um, and so let me just grab this result that we have here and we can copy that. Weird, I don't think it copied. There you go. We'll take this guy and we'll kind of talk about how to convert that into polar form, right? So if you kind of recall, this is, right, if you have some kind of complex exponential here, you can kind of convert it into polar form. And what we kind of want to do is take this complex part down here and kind of turn it into rectangular coordinates here, or this polar form. So this is going to be x squared plus y squared, and you take the square root. So this is the same as, oops, I take my real part, I take my complex part, and I take the square root. All right, and if you want a good way of visualizing that, kind of what we'll look at pretty soon here is we have a real axis and an imaginary axis. And if I take a real part, right, maybe this has distance r, and I take an imaginary part with the magnitude omega L, right, this kind of forms a right triangle, and you can determine the magnitude of this guy, just from the Pythagorean theorem here, right? And so that's this quantity, right? So if we wanted to convert our complex expression here into polar form, we'd take the square root of the sum of the squares. All right. And so we don't stop there. We also need to figure out the angle. And so the angle, right, this angle here is given, right, if that's our theta, we know that this height is omega L. So our theta is given by the tangent inverse of omega L by R, right? So going back to this guy, we have our e to the j times minus tangent inverse omega L over R. And this negative sign comes from the fact that this complex number is happening in the denominator. So we need a negative term, or sorry, a negative sign there because our exponential is technically in the denominator here. And so that's our expression from current for current. Um, and this is actually the same result that you would get from doing all the differential equations using the differential equation approach. So it's kind of reassuring that you get the same result in less than a page and a half of mathematics here. But it does require you to recall some complex number theory, or at least learn it if you haven't already seen it. Out of curiosity, have you seen complex numbers at all?
Yeah, it was like back in high school a little bit,
Okay, yeah, I figured.
that I worked with it. So
Yeah,
yeah.
right. So
I have
I
a
don't.
question about the that last term, the e to the j,
Yeah.
tan. So is that kind of just taking like we act like kind of like the denominator is
Mhm.
like that r e to the j theta, and
Right.
then we're
Yeah, j
transforming
omega
it
L
into
there.
that?
Yeah, exactly.
Okay.
Um, so they've got it written like this, but basically what's happening is this exponential term is in the denominator completely, which is where this negative sign comes from. But
Yeah,
yeah, so again, we're just converting this into um, rectangular coordinates,
got
uh,
it.
right? Because or is that polar? I kind of get mixed up on. Let me see. So it's converting exponential. Wait. Oh, so it's two exponential form. So it is in rectangular coordinates here, right? And that's kind of, I drew it out there. And then they're converting it into um, exponential or polar form. Anyways, so that's kind of like the motivation that, behind using Euler's equation to solve these things, right? Because if you were to look at the solution from the differential equations approach, it would be much more difficult. Um, And so that kind of leads us to the whole idea of phasors. So we'll talk about phasors here. And the general idea with the phasor is that we can kind of abstract away these sinusoidal functions into, right, if we instead consider this complex exponential forcing function, um, we can take this to actually just be, right, because technically, in a physical system, we'll actually just be driving it with some kind of sinusoidal function, but we can take that sinusoidal function to actually just be the real part of our exponentially driven, and I've got it written like this here, this complex exponential forcing function. And so we can actually write these in kind of what's called this polar form, or it's not polar form, sorry, the phasor notation here, where we just have the magnitude of our, sinusoid at some angle theta. Um, right, so we will start expressing voltages and currents in this kind of phasor notation, right? Again, these two will typically have different phase angles associated with them, but we'll kind of see for a resistor, they actually have the exact same phase. Um, all right, so let's take a look at, on that note, let's take a look at resistors. So we know by Ohm's law that, um, sorry, so I'm just going to label this section as phasor relationships or circuit elements. So first we consider the resistor. So by Ohm's law, we know that all right, this V of t is equal to R times I of t. And so if I were to go and write these in their phasor forms, so if I have some V sub m e to the j omega t plus theta v is equal to R times I sub m e to the j times the quantity omega t plus, they've got it theta I here, right? So again, these are distinct phase angles. I can actually go and cancel the j omega t terms here, and I'm left with Bm e to the theta, sorry, j theta v equal to R times I sub m e to the j theta I. And so right off the bat here, we can see that the angle, or sorry, the phase associated with the voltage must be the same as the phase associated with the current, because there's no kind of like additional phases going on here. So V is equal to R times I. So they've got this kind of like boldface notation to represent these phase angles here. Um, so here we can see that the two phases for voltage, between the voltage and the current through a resistor are going to be equal when driven by a sinusoidal source. Um, and if that's confusing right now, let's just kind of step through what it looks like for an inductor, and it might make a little bit more sense why, right? I make this claim that these are the same phase angles here. But if you have, again, if you have any questions, feel free to stop me. So let's just look at the inductor. So again, we have our inductor equation that relates current and voltage. So this is given by V of t, given by L times di by dt. And again, if we take our phasor notation I'm taking the derivative now of this complex current, and as I take the derivative of that term, I'm going to see again that a j omega pops out. So I'm left with j omega times L times Im, and this whole thing just stays j raised to the, or e to the j omega t plus theta I. Um, and I proceed by canceling out the j omega t's again. So I'm left with v sub m is given by e to the theta v. Vm times e to the theta v is equal to j omega L Im e to the theta I. And so
Is there a
here,
J theta for the for either of them? Is it
um,
or is it just theta?
it's just theta v, right? What I'm doing is I'm canceling out the j omega t's here.
Oh,
Yeah,
right,
so
right,
I'm kind
right.
of like dividing through by the j omega t's.
Okay, okay.
Yeah. So I divide through by that, and I'm left with this. Um, and this looks very similar to what we had up here with the resistor, but the only main difference is I now have a J. And what this J does is it actually causes um, a phase shift. Because if you recall, um, by Euler's identity there, we can actually show that J is 1 times e to the j times 90 degrees. Um, right, so if I go and use that, oops, move that up here. So if I use that, I'm left with this, where I have e to the j times 90 degrees omega L Im e to the theta I, right? And if I combine these exponentials, I have omega L Im e to, I'm adding these together, right? So theta I
Hmm.
plus 90 degrees. Um, and I'm missing a J here, like you had mentioned, but not seeing where. J times theta I. Oh, yeah, I'm missing it here. Sorry. So there's J's here. Maybe that's what you're trying to point out, but
Yeah, I think that
yeah,
was what I was
okay,
trying
yeah,
to
you're
get
right.
at.
Sorry, I forgot to distribute these J's. You're right. Okay, so yeah, that's where those J's went. Um, so this is going to be J times theta I plus 90 degrees. Is this review from E&M, or you
No,
haven't seen this yet? Okay.
no, we haven't. I don't
Okay.
even think we're gonna cover this at all.
Yeah.
I
Okay,
we're
cool.
yeah, we're gonna cover like RC circuits and then
Hmm.
we'll get into magnetism and then that'll be
Okay,
it.
cool.
But yeah.
Gotcha. Um, all right. So here you can see that the phase is clearly leading by 90 degrees. Um, and in this case, the voltage, right? And one way I like to think about this is civil, um, right? So when we're looking at an inductor, V is actually leading I by 90 degrees. And when we get to the capacitor, it's actually the current that's leading by 90 degrees, right? If we look at it that way. Um, right, so the voltage leads current by 90 degrees for the inductor, for inductors. Um, I'll just kind of box this guy here. And so that's for the inductor. Kind of like the next thing we would look at typically is the capacitor. I'm just going to give the result here, right? So if we use the defining equation for the capacitor, we can kind of show that the current, oops, and this would probably be good practice for you to try out. Second. Oh yeah, there's that J again. So here we can see there's that J, so it's going to cause that to lead, or 90 degrees to pop out up there. So the current leads voltage by 90 degrees for the capacitors. And so these are general statements. Um, all right. So with that, kind of like a summary of these results, um, they have this boldface notation for the current, J omega C times V. And again, that whenever there's an underline, there's it's kind of like a boldface in the text. And then we have kind of like the equation for the inductor, right? So V is given by J omega L times I. And then for the resistor, we just kind of have our good old Ohm's law, I times R. Or I guess they have the function of time last there, so R times I. Um, and again, these boldface or like underlined expressions are just shorthand for these complex exponentials with some magnitude there. All right. See how we're doing on time. So it's 10. So let me see. I had an example that I wanted to crank through. I had two more examples I wanted to do. So let's kind of see where we get. Um, so let's just quickly talk about impedance. So impedance is a generalization of resistance. And if we have our passive elements R, L, and C, they have impedances. I'm going to call this Z sub R. And then if we have Z sub L, this is going to be omega L. Right, sorry, J omega L. And then we have Z sub C, which is 1 over J omega C. And so impedances act a lot like resistances. So they are additive in series. So if I had, for example, a resistor, then an inductor, and then a capacitor in series as so, I could transform the elements right into their impedance form. And I could add these together to get an equivalent impedance, which in this case is going to be R plus J omega L plus 1 by J omega C. Right. And just like resistance, they sum the exact same way in parallel. But you know, when we had resistances, we had also defined the idea of conductance, right? Where G is 1 over R is conductance. Oops. say conductance, and that was additive in series. Sorry, not in series, in parallel. And we have a similar concept, right, in these frequency domain representations, but instead of conductance, we call it admittance. And so admittance Y is given by 1 over Z. And you'll need to recall that, these are complex valued, so it's typical to kind of represent them as these boldface notations here. Um, so again, if I had, for example, R, oops, all of these guys in parallel, right? So this is going to be J omega L. So then if I look at the admittance of these guys, so Y sub R is given by 1 over R. Y sub L is given by 1 over J omega L. And Y sub C is just given by J omega C. Right, so if I write these all in terms of their admittance, I could sum them up and determine the total admittance there. So this is going to be 1 over J omega L. This is going to be one. This is going to be just J omega C. And so this is kind of just like for formally defining things. I typically don't use admittance in practice, but it's good to kind of be aware of it and how it has similar properties to conductance, and it makes solving circuits in parallel a little bit easier. So it's good to be aware of these things. I'm not going to actually write down the equivalent admittance there in the interest of time, but um, so real quickly, let's run through this example. This is example 8.9. So they've literally got that kind of circuit that I drew out before with actual values. So this is 25 ohms. This is 20 millihenries. This is 50 microfarad. And we determined that the impedances Z sub R is given by 25 ohms. Z sub L is given by J omega L. And one thing I didn't mention here is that the source is at 60 hertz. So if we've got 60 hertz, then our J omega L, right, is 2 pi FL, which is J times 2 pi times 60 times our 20 millihenries. So they calculated this out to be J 7.54. And one thing to note, right, is impedance is given units of ohms, even if it's complex, right? This is a imaginary number, but it's still in ohms. And lastly, our capacitor given by J omega C, 1 over J omega C, 1 over 2 pi times 60 times 50 e to the minus 6. And so they calculated that out to be minus J 53. Oh, sorry, I missed the J. Minus J 53.05 ohms. And so if you stop right there, right, you might be wondering where that negative comes from. That comes from the idea that 1 over J is actually equal to minus J. So it's a little nuance that um, comes up quite a bit. And, just going back to Euler's relation, you can kind of figure how that works out. Um,
So
okay.
impedance is always in ohms.
Yeah, it's always in ohms.
Okay. Okay.
So then if we go and figure out the equivalent impedance of this entire network here, right? If I just call that Z, then that's just going to be the sum of Z sub R plus Z sub L plus Z sub C. And if I add up all those guys together, I'm left with 25 minus J, 45.51 ohms. All right. And then last but not least, we want to kind of figure out the current. So the current, generally speaking, is given by V divided by Z, right? Again, this is a lot like Ohm's law, right? Where you had I is V over R, but now we're working with a bunch of complex numbers all over the place, right? So um, they've got the current here. I'm trying to figure out where they got this 30 degrees from. Oh, I missed that part of the question. So they defined the voltage to be 50 cosine omega t plus 30 degrees. And then they defined the frequency to be 60 hertz there. So I completely glossed over that part of it. But going back here, now we've got 50, right? The magnitude of this cosine function is 50. It's at an angle of 30 degrees. And then the impedance is 25 minus j, 45.51. And you could very well just stop right there. Um, but you could also kind of convert this into a magnitude and an angle, right? Again, to get the magnitude, realize that it's a triangle. You got 25 on the real axis, 45. It's going negative, but it would kind of be the same magnitude, I guess. So 45.51 there, kind of get your angle from there. And they've calculated that out. Right, so we're looking at 50 at an angle of 30 degrees up here, and then 51.93 at an angle of minus 61.22 degrees. And you could actually plug this into most scientific calculators and kind of get a result there. So I won't go through the math and actually do that, but that's kind of like the final result here for for the current. I know it's a lot of probably funky math that you haven't come across before, but it's kind of the world that we live in. Um, so I did want to do another example, but we didn't really get into talking about phasors. I'm just going to talk about it really quickly and, just like the whole concept of phasors, generally speaking, just so that we can kind of move on from it. Um, so like we had mentioned before, for let's just talk about phasors really quickly if you've got the time here. So, right, we had these expressions for um, impedance. So I'll just have this Z sub R is R times I. Sorry, not the impedances. Let's talk about the voltage and current relationships. Right, so that's for the resistor. For the inductor, we had j omega L, or yeah, j omega L times I. And then for the capacitor, oops, we had 1 over j omega C times V. Let me just make sure that's, yeah, so that's more or less what we had, right? For the capacitor, we had that, sorry. So this is just j omega C times V. Um, so if we kind of look at what this looks like in the real and imaginary axis, if we look at firstly the resistor, right, I have presumably some voltage, and then this current is actually going to be also, in the real axis here. There's no angle associated with them. But then if I look at the inductor, maybe I just call this voltage my reference. The current again is going to be 90 degrees, right? Um, Shifted from the voltage. And again, going back to this civil, if I look at from the perspective of the inductor, my voltage is leading the current. And so what that actually ends up looking like, and I kind of messed it up here, right, is if my voltage is there on the real axis, right, at kind of like a 0 degree angle, my current is going to be over here, right? So the current is actually going to be happening after the voltage. And let me just make sure I don't have that mixed up because that looks wrong. It's been a while since I've admittedly I don't use phasors on a day-to-day, so um this just makes sense to me, right? Because the voltage is at 0 degrees, this is current, and it's happening at a later time, basically.
Wait, but inductance, it leads voltage, right? So would it come before?
Let me see what they have. That's again, it's not something I do day to day. No, so yeah, I have that right. So um, the current for the inductor, yeah, just write it like that. Um, I'm glad I had it right there because that's kind of an important thing to. So the voltage is leading the current. And what you can kind of think about here, right, is, I mean, yeah, it looks like, hold on, how do I explain this? You can imagine like we're rotating, right, around this guy, right?
Mm-hmm.
So in order for the voltage to lead, it needs to be ahead in that rotation, right? So if I
Right.
were to kind of rotate, maybe the voltage is occurring at 90 degrees, right? Then the current would be back here at 0 degrees, right?
Yeah. Yeah.
Right. So yeah. So yeah, it is that way.
Yeah, I understand. Yeah, okay, I
Okay.
get how it
Yeah.
goes down. Yeah, yeah.
Gotcha. Okay. Yeah. It's a tricky concept, and honestly, if you
Mm-hmm.
mix up the directions, it's like in an interview or something, it's not a huge deal. You just kind of need to remember that for the inductor, right, the voltage is leading, and then for the capacitor, you got the current is leading. So it's kind of just the other way around, right? So if I keep my voltage at this 0 degree reference, then my current is actually going to be leading, right? So it's going to be up here by 90 degrees, and it's always 90 degrees, right? Because we've got these J terms here, if that makes sense. Um, so going back, because I know it's been a while since you had complex number theory, right? This unit vector is kind of just what we're used to, but this unit vector is J. Um, if that kind of makes sense. So whenever I have
Yeah.
a complex part, yeah, so it's just going to be adding in the imaginary direction there,
Mm-hmm.
right?
Yeah.
So that's a unit vector of one, that's a unit vector of J. Um, but cool. So I think that's all I wanted to talk about here, unless you got any other questions. I'll probably stop the recording. Kind of fumbled that last part, but